discuss too. Okay, just now it's okay. So one of the different motivations that I have been so far is applying this different technique in clinical applications. So at the beginning, I tried to understand how the brain is changing when you are getting older in a healthy lifespan. But also, for example, I am interested in understand how a brain is changing, for example, to a neuropathology. And in the last 2 years, I am also really keen in understand these different neuromodulation techniques, not invasive one, as for example, the transcranial ultrasound stimulation. And this is relevant because that could be like a replacement for the different pills that are not working for all the participants. So the final goal here is being able to use all these different complex techniques and go also to help the patient and doing these different neuromodulation techniques at the end. So far when we are trying to analyze or characterize the brain, we have different ways in order to do that. And one, for example, is using MRI machine. So you can obtain two different type of data set here. You have like the structural or anatomical information. And in the other hand, you have like this statistical world. In the case of the structural connectivity, we talk here about pairwise analysis. So you can observe, for example, two different brain regions, and you have like the axon connecting two different areas. And in the case of the functional information, you take different time series, and in this case could be, for example, functional MRI. The studies that I will discuss is using functional MRI, but you can have EEG, MEG, calcium imaging also, modeling, and so on. And the classical way in order to analyze these different quantities so far is been using pairwise analysis. And in this case, you can create, for example, this matrix, and a position here will be the Pearson correlation between these different two time series. But in the several last years, there have been a lot of researchers doing the effort in going beyond this pairwise analysis. So there is no reason to think that the statistical interdependencies are only between pairwise. So you can look 3 different brain areas, 4 different brain areas, and so on. And of course, in order to do that, you have here, for example, information theory in order to create these different concepts. When we are going, for example, for one variable to 2 different variables, in this case, brain information, until 3 of them. And in the case when you are having 3 or more, you can talk about this different concept of redundancy and synergy. I will just be a little bit brief in this part. But for example, here for the case of triplets, you can just look the sign of this quantity and observe if they are predominated by redundancy and synergy. And the good news is the story is not ending here. The mathematician loves generalizations. So here in 2019, we have this amazing result of Pedro Mediano and Fernando Rosas, where they propose the O information that you can start in the case of triplets and continue generalizing and obtain this quantity still, just looking beside the generalizations in terms of redundancy and synergy dominated. So I would like to discuss a little bit about Ratatouille. And why Ratatouille? Because I would like to fix the concept of the redundancy and synergy. So I would like to think, if you have seen the movie, about Remy when he was trying to explain this amazing cooking experience to his brother. It wasn't successful, but the experiment is really nice. So in this case, you have Remy with a cheese and also a strawberry in his hands. And he did this simple experiment. So in one case, you have here trying the cheese. So the experience was nice. You are having a flavor, a smell is really nice. And then you also can taste here the strawberry. And the experience was kind of similar. The smell, the flavor, the texture was really nice, but nothing too impressive. But in the other case, you have this experiment here in the right, where he took the 2 of them together, the cheese and the strawberry, and he had this amazing and fantastic experience. And of course, we can relate these 2 concepts with, the redundancy and the synergy. I don't know what is happening with here. Yes, right, with the redundancy and the synergy. So far, we have these different high-order interactions, and I would like to ask you if you think the high-order interdependencies are important or not. And I hope that if you are not already convinced of that, you will be convinced at the end of this talk. And I will start with this pioneer study in healthy aging. So for example, here in the first figure, we have this result of Borja Camino Pontes in 2018, where he analyzed triplets in healthy aging. In the yellow color, we have here the older population. And they observed that the older population was more redundant than the youngest one. Here also you have the distribution of these redundancy values. After that, we generalized this using the O information going from triplets to the whole brain. Here the yellow color is still being the same, the older population. And again, we observe that the older population is more redundant, independent if you are looking triplets, four-brain regions, and so on. And after that, we move to a dynamic mean field model in order to propose a mechanism, in this case, using the changes in the structural connectivity in order to observe and explain these changes in high order. And we reproduce this using a whole brain model too. So after the healthy aging, we can move, for example, to this paper of Andrea Santoro, and it's not only because my current boss is there, it's because this paper is really nice. So in this case, you have this generalization of this quantity of the edge co-fluctuation across time. But now you are also doing not only for pairwise, also going to triplets and so on. And in this case, you can also extract different topological features. In this case, we have these topological features here. And here we have the features from information theory. So first row is high order information. And in this case, we have different pairwise analysis, in particular here, the Pearson correlation. So in the x-axis, we have here different regimes of time series. So if you look by eye, these different time series there are different, and you would like to have a quantity that is also able to distinguish between them. So here we have this value that is the bigger the better, and we can observe here that the Pearson correlation is not doing that well, but in the case of the high order analysis, they are doing really, really nice. So another point for the high order interactions here. With that, I would like to move also to neurodegeneration. And in this case, we have this paper led by Ruben Herzog in 2022. And in this case, they not used only functional MRI data, he also used EEG data. And he characterized Alzheimer's disease versus control condition and frontotemporal dementia versus control condition. And they observe here in the x-axis the interaction orders with the dashed line, the optimum, to characterize and predict these changes. And you can observe that you need higher order interactions in order to characterize better these conditions. So finally, with this, I would like to go to the simple example. At the same point where we talked in some years ago about static functional connectivity, and we move to the dynamical functional connectivity, we have here the same idea. You can move also to this dynamical high order where you include also the time. And you need to be careful in this case, because when we look the O information in this nice preprint by Maria Pope and also Thomas Barley, you can observe that the O information is mostly redundant. You have like low synergy in this case. Also, you have here the fraction of this synergy for triplets that is really low. And in the other case, we have here another message, because if you look the predominance of the redundancy or the synergy in different parts of the brain, you have, for example, that motor area that can coexist in terms of redundancy and synergy. And so far, using this static measure, we have been saying, for example, that you have predominance that by the redundancy in motor areas and so on. So this is like a nice result and something to have in mind too. So far, I would like to ask if the high order interdependencies are important, and I expect that you are convinced that they are. So far, just to summarize what we have been talking so far, we have these different worlds that are complementary, that are the pairwise analysis, the high order analysis. Here you have all the different techniques, the math, the nice toolbox in order to quantify segregation, integration quantities, but also you can move to the high order interactions where you have this world of topological data analysis, multivariate information theory, and you have several different applications. So here, for example, we are just showing some of the examples. And I would like now with that move to the transcranial ultrasound stimulation, in particularly in macaque. So this is part of a collaboration with the Professor Marcus Kaiser, also Pedro Mediano, Cyril, and Mo. And in this case, here the only important part is this one and that one. We have 3 different macaques in 3 different conditions. Control condition, meaning we are not applying any stimulation at all. SMA, you are applying a stimulation in supplementary motor area, and FPC, you are applying a stimulation in frontal polar cortex. So the question here is, can we use high-order interdependencies in order to explain these changes? And in this case, we are only looking this panel here that we would like to observe per each brain region if after applying the stimulation, the control condition is shifting to the redundancy or the synergy. So in this case, we are showing the result for the frontal polar cortex, that is this area that you see here, and the result for the 3 different macaques. In this case, you have different results switching to redundancy and synergy, mixing effect, but the nice result for us here was that you are able to have the same effect across 3 or 2 different macaques, changing in the same direction. And when we move here, for example, to the supplementary motor area, doing the target here, you have different patterns compared with the previous one, but also even when you are having heterogeneous behavior, you can have exactly the same patterns in the 3 different macaques. That was, for us, was really nice because so far this type of data set was used with the classical pairwise analysis and only observing group analysis, not at the level of individual. And also, just to mention briefly, we did some analysis in order to show previous research by Andrea Lupi, showing that the redundancy is more related with the structural connectivity, the synergy also with the distance, and also how they are changing after you are doing the stimulation, and they are differentiated depending on the stimulated target. So if you would like to have a look more about this result, this is the paper of this. And here we are showing the different effect when you are stimulating in frontal polar cortex or the supplementary motor area, and also the different characterization and correlation with the structural connectivity and the Euclidean distance. And so far here we would like to mention that these effects are depending on the stimulated target. And also you are changing here the intrinsic topology that you have when you are doing this stimulation. So I would like to go after that. Sorry, I think.
Marilyn, we have a quick question in the chat. Can you mention where you get the data sets that you used in these analyses?
Yeah, in the macaque data was a collaboration with Oxford University. Yeah. Okay. So yeah, in this case was an experiment, I don't know if conducted or just he provided the result, but Jerome Salet. So that's why we have this type of data set. I think that's the only one, yes. Okay. So, well, with that, we move to the transcranial ultrasound stimulation, and this is part of the work that, well, Cyril and Mo, they did the experiment in humans participant in the University of Nottingham. So this work is part of the group of the Professor Marcus Kaiser. And in this case, we are truly interested in this type of stimulation because it's new. So since 2013, you only have less than 50 experiments. There is like worldwide 120 centers doing this type of experiment, and in the UK only 5. So we are doing some of them, and that is really cool also for us. So in this case, we are now, the group is growing. Now my current PI is Giovanni Petri, but we are still collaborating with Marcus, Cyril Mo, also Pedro, Fernando, and Carlos and Enzo, that they are also expert in whole brain models. And in this case, well, I just didn't mention this part, but we have like two different experiments. We have one experiment stimulating the inferior frontal cortex, and in the other one, we are stimulating the thalamus. So the question here is the same. We would like to analyze how the different networks are changing when you are doing the stimulation in one brain area. And here in the case of the stimulation in the inferior frontal cortex, we are observing changes in the redundancy or the synergy, increase or decrease in color red or blue. And in the case of the thalamus, the same story. You have some changes in the redundancy and the synergy and patterns that are differentiated depending where you are applying the stimulation. So one result that was nice for us also is when you are doing the stimulation here in the inferior frontal cortex, we are observing more changes in frontal areas. And in the case of the stimulation in the thalamus, you don't have that same pattern, but also you are recovering here, for example, in the changes of the synergy, the difference in the right thalamus, that is the stimulated target too. And with this idea in mind, we were interested in propose a model in order to explain these changes. And we went to this nice paper by Caio Seguin in 2023, where they use a different type of data set because are a drug-resistant participant. So in this case, you are able to do the stimulation and measure this corticocortical evoked potential. But the important part here is that they are using here different models in order to go for this based in efficiency to those based just in pure random walks and something in between. So we would like to know if, for example, the shortest path is the one that is more explanatory in our model, or are the random walks or something in between. So, for example, here we have the communicability, that means that is this broadcasting process. So if you have more path in order to go from the source to the target, you will potentiate the answer of this stimulus. And you have, for example, the search information, that is the amount of information that you need to bias this stimulation to go to the shortest path. So in this case, we test the shortest path efficiency, the search information, the communicability, because they were relevant in this paper in particular, and they also show that there is not the shortest path efficiency, the most explanatory, is something more in between the search information and the communicability. And also, of course, we test the distance because it's relevant for the case of the stimulation. And so far, I will just show the ones that were statistically significant for the two different targets. And in this case, when we are stimulated, no matter if the inferior frontal cortex, the thalamus, we observe that in the case of the distance or the communicability, we have these different effects that were statistically significant and more explanatory. So with this idea in mind, we would like to propose a model, a dynamic mean field model. Oh, sorry, not a dynamic mean field model, a Hopf model, in order to produce these effects. And at the end, the experiment was easier. We were swapping the area that we were stimulating and also including this heterogeneous parameter using the model based in communicability or distance. And we would like to know how the brain is changing when you are doing the stimulation. So there is a lot of information here. This is also part of the work in progress that we are writing so far. But this alpha parameter is how much are you targeting the area. So I would like to focus here that we are doing the stimulation here in the inferior frontal cortex, the right thalamus, the result for the redundancy, for the synergy, the same in the other side. And I would like to focus only in the redundancy so far in the two cases. And here, for example, we have this area in red. That means when you are swapping just a little bit the area, you are not seeing any difference. And also, I would like to mention here that in the case of the changes with these alpha parameters that I will discuss briefly, when this is negative, we are having also the biggest correlation in the case of the redundancy. So in the case of this parameter, when you move this parameter more to the left, you are adding more noise into the system. This is a Hopf model. In the case of moving more to the right, you are adding more oscillations that are more synchronous at the end. So in this case in particular, what we are saying so far is we can relate this general change of the neuromodulation more with an inhibition than with an excitation. And also with this parameter, you can observe that at the beginning when the swap in the area is slow, you are just changing the area, but you are starting increasing this change and you are changing across different parts of the brain. So I think I have some question in the chat.
Yeah, Bunmi was asking for clarity on what redundancy is. You provided a brief introduction at the beginning, but could you give us a refresher on the distinction between redundant versus synergistic information?
Yeah. Okay, yes, sorry for that. In the case of the redundancy, we are saying that information that you can obtain no matter which of the sources are you observing. And in the case of the synergy, it's like the emergence. In this case, it's a little bit more tricky because we are computing the redundancy and synergy and didn't say that using two pair of time series, but we are including also the time. So we are doing sort of time delay mutual information and splitting that in redundancy and synergy. But for example, if we have these two time series that are fully synchronized, we will have like a lot of redundancy and zero synergy. We show some example in the macaque paper. When you are switching, for example, one of the time series, you can reduce the redundancy and increase of the synergy. And that is something that we will expect to be happening in the brain because you have this coexistence of redundancy and synergy. So in this case, that's the way of seeing the high order, also including this change across time, more than taking the generalization of the different time series static one. I don't know if that is clear. Yeah. Okay, I think. Okay, thank you. Okay, so what I was saying here, yes. So in this case of experiment, at the beginning, when we use the different parameters of the stimulation, in theory, you are doing an excitatory change, an excitatory neuromodulation. But we think with this type of model, you are also to explain if the overall effects are doing this excitatory effect or more based in inhibition, as we are saying here with these preliminary results. So this result will coming soon because we are still writing this. And also, I would like just to mention briefly that in order to continue in this line is relevant and also I think it's really interesting using these different whole brain models in order to also taking into account communicability models and putting these different mechanisms in order to explain the high order changes that we are trying to propose. And yes, I have here the equation and also the model that I thought that I put before, but not. So when I was talking about this bifurcation point, that is this parameter that we are moving in the model more to the left or more to the right, we are doing more noise or more sustained oscillation when we are doing this swapping area. Yeah. So I would like to finish in thanks to these amazing networks of collaborators. And also, thank you very much for all of you for your attention. And please, any question, don't hesitate to write me now. And you can also write me to my email. Thank you very much.
So we have plenty of time for questions. I see one in the chat already. I know there are also lots of network neuroscientists in the audience that I imagine might have some questions. Thomas, feel free to unmute yourself if you'd like, or if you don't, you can, if you don't want to unmute, I can read your question for you. Up to you.
Oh, no, it's fine. Thanks for the talk, Marilyn. It's always cool to see what you're working on. Uh, could you go back one slide to the bifurcation?
Yes.
Did you find any? Oh no, what forward?
No, one forward.
Yes. Yes. Okay. So the bifurcation point in your HUPF model. Uh, Forgive me if I missed this, but did you find any relationships between synergy and sort of proximity to the bifurcation point? I know there's a lot of interest in linking synergy to ideas of criticality and these kinds of phase transitions. Did you do that analysis at all?
Yeah. I think my mistake here is I didn't put this slide before, but just to mention, you are asking here about the bifurcation point. Just a second. Okay. Yes, I have the equations that I need. So in this case, the stimulation, we are moving the bifurcation point. In this case, doing this stimulation positive or negative, that means you are moving more to the right or more to the left.
So you're
that is
actually
the alpha
moving,
parameter.
you're moving
Yeah,
the
actually,
bifurcation point itself, not moving where
exactly.
you are relative to it.
Exactly. We are moving
Okay.
the bifurcation point, and in this case, we are just moving the bifurcation point in the area that we are doing the target. So we move this parameter for the case of the inferior frontal cortex, or in the model of the thalamus for the thalamus.
Okay.
So that's why I said this was my mistake, because I thought I put this before and I miss it here. But in this case, in the x-axis is when we are moving this bifurcation parameter to the right or to the left. And in the case, you can see here that near to 0, we are not seeing that much difference. So you need to swap harder the area in order to observe these differences. So I think in order to see these changes near to the bifurcation point, it's important not to include only a one, changing only the area, but also maybe a neighbor near to the area that you are changing. So probably that can help to understand what is happening more near to the area, more than doing only the change in that particular area only.
Okay, awesome. Thank you very much.
Thank you.
If others have questions, feel free to unmute yourself.
I got a quick question. I'm not coming from the background that the talk was about, so I'm trying to understand the redundancy a bit better. If you have a network built on, say, conditional independence tests, right, where you put an edge between two nodes, condition on all the other variables, which is basically all the other information within the nodes that you have. Can you think about redundancy this way, that if your network is based on this conditional independence test, then you expect your redundancy to be 0?
I'm so sorry, I think I missed the point. Can you explain it again? Sorry.
Yeah, so like there are different methods that you can build a network on, right? So one method that you can build a network from time series is that you would build it based on conditional independence test, where you put an edge between two nodes. If there is, if you bring all the information from the other nodes, and then it doesn't explain the relationship between those two nodes, right? So if I build a network based on conditional independence, does it mean that the redundancy for that network should be 0?
Can you maybe explain me a little bit more what is conditional independence? Because I just can imagine that with, for example, if in this case we have two time series that are completely unsynchronized in all the time.
Mm-hmm.
But I don't know if that is the thing that you refer to, because in that sense, I will expect to have no or really low redundancy.
Mm-hmm. Right. So for that sort of network to build, you need more than 2 time series. So at least you need a trace because you want to look into, let's say, nodes A and B given a node Z, and then to see if there is an edge in between those. Okay, I see.
I have a question while we give others a chance to gather their thoughts a bit. So this is about, I think the first results that you presented with the macaques, where you had the brain images showing which regions became more or less synergistic or redundant. And I remember that you mentioned that you had a result related to the Euclidean distance, but I wonder also, like, if the regions where you saw big increases in synergy or redundancy, are those regions that have structural connections between them? Like, could it be the case that we're seeing these information dynamics flow across structural connections, or is it happening over regions in the absence of structural connections? So there's something about the co-fluctuation between them that's really informative.
Yeah, that's a really good question. And to be honest, we didn't do like the overlap between them. In this case, we were more interested just in observing Euclidean distance in particular and the structural connectivity in other side, but we didn't see what was happening, for example, when we just observed the structural connectivity there. But that's something, yeah, really interesting to have a look at. I agree with that.
Thank you.
Hi, thank you so much. Can I have a very simple question? Sorry, I don't know anything about brains almost. So I would like to understand, like, how do you know, for instance, that there is a function? So I mean, what I understood, correct if I'm wrong, is that for synergy or redundancy, you have a function of an activity, right? So how do you know that there is I don't know, someone is reading, and then you know that particular regions are reading, and that's why you have redundancy or synergy. So how do you model the function with the redundancy and synergy?
I think that I can relate, for example, the redundancy and synergy with the results of Andrea Lupi or Thomas Barley, for example, where they can give like a meaningful of the different brain regions that are more predominated by one and the other one, going in that line with cognition, sorry. Because I agree that in this line, we are mostly doing different changes in different brain areas, but we are not explaining with the cognitive feature itself what is happening here, right?
Yeah, so I wonder, like, if it's something dynamic, right? If it's something like, if I'm reading, I can use different areas to understand. I don't know, maybe I'm completely wrong. But I wonder, like, how I could use different regions to do the same function of reading, or, like, how this could be interesting to understand, like, how we change the regions. But maybe it's because I'm not from the area, so I'm not quite catching, like, how the function of someone doing something is related to the brain activity. You said that it's about the papers. I didn't read the papers, so I don't know. I'm sorry.
Sorry, in the case of, for example, the thing that you mentioned of taking different brain areas, this idea of integration of segregation in the term of pairwise analysis is something that have been done. I think with this idea of the high order, we are trying also to see a little bit the same, this coexistence of redundancy and synergy when you are observing these different techniques too. But it's something that I would say that is a work in progress. I haven't seen so far analysis using different tasks. I've been seeing mostly resting state functional MRI. So I think like it's part of the work also in progress to say something more in that line. I don't know. Yeah, please.
Thank you so much.
So I know Thomas has his hand raised, but we also had a question in the chat from Bunmi. You had mentioned a couple of papers sort of at the beginning of your talk to generally learn more, but do you have other recommendations for where people can learn more about this kind of work in addition to your own?
Sorry.
Or can you go to like some of your earlier slides just so people can sort of understand the context a little bit better?
Yeah, sorry for that. Yeah, for example, I think these different paper, Maria Pope, Thomas Barley, you have a lot of different papers. There's also in the case of Ruben Herzog, if you would like to go to Alzheimer, neurodegeneration, there is like Andrea Lupi, he has like a bunch of different papers in consciousness, cognition, evolution, doing the analysis, not only in human analysis, but also in macaque analysis, showing that, for example, in the case of the synergy, you have more synergy in the case of the humans than in the macaque. That could be something interesting to have a look to. So also, yeah, Andrea Santoro has like two different nice papers where he did the first example that I show here. This is just only different time series, but he also did epidemic, economic data, and brain analysis in one of the applications, also observing resting state and comparing the resting state between task itself. So, yeah. I think that's, yeah.
Well, and then Thomas, if you want to go ahead and answer or ask your question, go for it.
Yeah, sorry for coming back in. But so quick question. I imagine you're using mostly Gaussian estimators, right? That's pretty standard in this kind of work.
Yes.
So
Yes.
I understand redundancy in the context of Gaussian estimators. It's you think of it as sort of analogous to synchrony. How do you sort of understand synergy specifically for multivariate Gaussian variables, right? In the discrete case, we have the logical exclusive OR gate, but what is Gaussian synergy? Since everything is fixed by the pairwise covariance matrix, sometimes I struggle to understand what this measure is in the context of Gaussian estimators.
Mm-hmm. Yeah, I think that is a tricky point, trying to reduce everything to the case of covariance matrix. I agree with that. Also agree with the point that so far we are saying that the both imagings are Gaussian-like. So in order to the estimator could make sense or not. But yeah, I agree that is an interesting point. And to be honest, I don't know how the result will change if we are not using, in this case, a Gaussian estimator, for example. In the case of the healthy aging, we did the analysis not only with Gaussian copulas in this case, you are still doing the estimation over the covariance matrix, even when you are not doing like the Gaussian assumption. But we tested, for example, the result using Kraskov or another non-parametric assumptions, and we obtained exactly the same result. But for the case of this type of analysis in macaque data, I'm not quite sure how they will change here.
Okay, but like, so if you give me 3 time series and tell me that they have positive O information, I can kind of understand that that means that the 3 time series are like copies of each other, right? They're like redundant.
Mm-hmm.
If you give me 3 time series and tell me that they have a negative O information, like what should I imagine in my brain, right? Are they synchronized? Are they desynchronized? Are they antiphase? Like, you know, what does it mean to have continuous synergy?
Yeah, to be honest, For me, so far, I can just relate it with something that is going in and out of synchrony, because that is the metastability regime that we can observe, like this coexistence of redundancy and synergy. But so far, I can understand the coexistence of the two quantities, more like to tell you, for example, why a synergistic regime of time series will look like this one.
Okay. Okay. Interesting. Thank you.
Thank you for that.
I have another question, but I'd like to give folks who haven't spoken up the chance to ask any questions they might have. If not, I mean, we have plenty of time for questions. I'm curious, given that you're looking at higher order interactions in the context of brain stimulation, what kinds of like applications you see for studying the like higher order information dynamics in the brain? Like, is this something you see having like practical use in like a clinical context, or what are your what's your thinking there?
Yeah, actually, now I am like trying to work in a grant for an early career researcher, and I have been dreaming about it. And it's like trying to go in the direction of the transcranial ultrasound stimulation that I am fascinating so far with that. And I think that the high order interaction can help to understand if the protocol are doing the neuromodulation in one direction or the other. Because you have these different patterns that, depending on the parameters that you are using in this type of neuromodulation, you know that you are doing one suppression or not across brain. But with the modeling itself, and also mixing with the feature of high order interactions, I have the feeling that you can go a little bit further and try to find an answer to that and explain if overall you are doing that effect or not. I think that could be really interested in order to go to this type of techniques too. And at the end, I don't know, going to apply actually to a clinical population will be even more amazing.
Thank you. So we have a question in the chat. How do your findings apply to the study of neurodegenerative diseases?
Oof. To be honest, when I was doing my thesis, we start with healthy aging, then we try to move to frontotemporal dementia, and exactly the same methodology as was done. We didn't have too much success. And I have the feeling that was because we were doing a lot of average. And in the case of frontotemporal dementia, for example, you know that there are particular brain regions that are changing. So you need to do different type of analysis. And in that case, I think that is the tricky part. You need to understand if the methodologies, or how to adapt the methodologies to the particular case that you are observing. That is, I think that is the most challenging part also. But in the same line, I'm also interested in going with these different techniques in the same directions, because we have, like, for example, several quantities, and sometimes you move a lot the methodology in order to go to the particular disease. But then when you try to compare, for example, Alzheimer's disease with healthy aging, nothing makes more sense anymore. So I think that is also the tricky part in order to go in that direction. It's one of the challenging.
Thank you. There's another question in the chat. Are there good places to get pre-collected data sets or simulated data?
Pre-collected data set or stimulated in terms of stimulation, or any case of?
Maybe like some of the models that you use in, so they clarified perhaps experiments already done by people. So if somebody wants to analyze a neuro data set, where might be a good place for them to find that data?
Yeah, I can say the Human Connectome project. You can use that data set that is already preprocessed. For example, start using the 100 unrelated subjects. But also you need to be aware that some of the reviewers don't like to have the same data preprocessed one and over again. But I think it's a nice data set still to be doing different analysis. And in this case, you don't have only a resting state, you have different tasks. So it's something to have a look, I would say. And in the case of our study in healthy aging, we have the data set open, the structural connectivity and also the time series, but only with 20 brain regions. And I think also, well, Carlos Coronel probably have some simulated data, Joana Cabral, that you can have a look of it.
So I have another question to fill the space as other people. Would you mind sharing the link to your open data?
Yes. Should I stop sharing to
Sure.
find the link? Yeah. Just to go to the web page. Okay. This is the one.
Very exciting. Thank you for sharing. So I had another question to sort of fill the space. So I'm wondering if you have, I know that task data is so much more complicated and involves a lot more than just resting state data. But I'm curious if you could sort of speculate on how you might expect the results to be similar or different for task data versus some of the resting state data that you've presented.
Yeah, to be honest, I don't have like any clue depending on the task, because so far the only thing that I have seen is the analysis of Andrea Santoro, where he observed that you can distinguish between the different conditions, but not what is happening in particular when you are observing one of them. So I have seen some of his results regarding to emotion, that I think that with different analysis in topological data analysis, you are able to distinguish high emotions in a movie. But I don't feel confident enough to move from that conclusion to the case of the multivariate information theory, to be honest.
Yeah, that's fair. It's a big question.
Yeah, I agree with that.
Well, we still have a few minutes before our time ends, so I'll give folks a chance to put together any final questions or thoughts that they might have. I'll give people a minute or so, and if not, we can end a bit early. I do want to emphasize it was a great talk, Marilyn. I really enjoyed getting to hear some of your recent work, your in-progress work. Is there a preprint coming soon that we can look for?
Yes, we hope so. We hope so in the following weeks we will have ready the preprint. Yeah.
Very exciting. Great. I think that might be all of the questions that we have. Thank you again for joining us for part of the Women in Network Science seminar series. Stay tuned for our next speaker in a couple of weeks. And we'll keep an eye out for your upcoming preprint, Marilyn. Thank you so much. And thank you everyone for attending.
Thank you for the opportunity and for the questions.
Of course. Bye.
Bye. Bye.